So we now continue the discussion on weak and weak star topologies. So the previous question was, so going back to this highlighted part here, when is the weak and weak star topologies coincide? And as we shall see, these are precisely the reflexive spaces. So let us define what we mean by a reflexive space. So a Banach space X is said to be reflexive if the canonical embedding Jx from X to its bidual. So recall that this is given as follows. So take an X in capital X and an X prime in the dual space. So let us emphasize here the duality pairing. So this is in X prime, X double prime. Now take note that this is nothing but the duality pairing between X prime and X. If this canonical embedding is surjective. So that is the image is the same as the bidual space. So we know that for every Banach space X, this canonical embedding is a linear isometry. Therefore, we can say that X is reflexive Banach space if and only if the canonical embedding is an isometric isomorphism. And for this, we have the following theorem. So let's start with a Banach space X. Then the weak topology and the weak star topology. Or I should say the weak star topology and the weak topology are the same if and only if X is reflexive. So the reverse direction follows from the fact that, of course, Gx of X is the bidual space and the definition of the weak and weak star topologies. The reverse direction is quite technical, and we do not provide it here. This was proved by James, that you can see a proof, for instance, in the book of Conway, or even in the book of Danforth and Swatch. So let us discuss in detail some properties of reflexive Banach spaces. If X is a Banach space, and it is reflexive, and Y is a closed subspace, then Y is also a reflexive Banach space. So to prove this theorem, okay, let's start with the goal. So the goal here is to show that the canonical embedding from Y to Y double prime is surjective. In order for Y to be reflexive. Of course, Y being a Banach space, we know this already because a closed subspace of a Banach space is, again, a Banach space with respect to the inherited norm. So let us pick an element in the bidual of Y, say Y double prime. So based on this, we define an element in the bidual space, okay, as follows. So X double prime, X prime, okay. So here X prime is in the dual space. What we do is we take the restriction of this element in X prime, and you can show that you can easily show that this restriction is indeed in Y prime. So therefore, we can take the duality pairing of this restriction to this particular element in the bidual of Y. So this makes sense. Boundedness follows, in fact, from the boundedness of Y double prime. And this dual norm of the restriction is less or equal to the dual norm of X prime. So the fact that indeed this is in the bidual space is left for you to verify. Now, the reflexivity of X implies that there exists an X in a capital X such that J of X is this X double prime. In fact, we claim here that this X is in Y. Suppose this is not the case. So by way of contradiction, suppose X is not in Y. since Y is a closed subspace, we can apply the Hahn-Banach theorem, or more precisely, a corollary to the Hahn-Banach theorem, to guarantee the existence of an x naught prime in the dual space of X with the following properties. So the restriction of this bounded linear functional on Y is 0, and that the duality pairing at the non-zero element X is the same as the distance of X with this closed subspace. Now, these two properties imply that, okay, let's start with the duality pairing here. This is the same as, okay, applying the definition of the canonical embedding for X, and since Jx, okay, is equal to X double prime, and then replacing here X prime by X naught prime, we get the following. So this would be, so going back to that, the restriction of X naught prime on Y, Y double prime. However, the restriction is 0, so therefore this is 0. So in other words, this implies that the distance of X and Y is 0, and Y is a closed subspace. This must be, and X is not in Y, this must be not possible. So this is a contradiction to X not in Y. Okay. So the assumption that X is not in Y is not valid, hence X must be in Y. So let us now prove the surjectivity of the canonical embedding in Y, of Y into its bidual. So let's start with an element in the dual space of Y. So we extend this to a bounded linear functional to the whole space X by applying the Hahn-Banach theorem once again. So there's a bounded linear functional in X such that the restriction is equal to Y prime. Then, okay, let's start with this duality pairing. Take note that Y prime is just the restriction of X prime in Y. And take note, according to the definition, okay, here, of X double prime, this is X prime, X double prime. Since X double prime is the image, okay, under the canonical embedding of this vector, or yeah, of this element X, the one that we constructed here, okay. And according to the definition of the canonical embedding in X, this is the duality pairing of X and X prime. We know that X is in Y, so I can write this as the duality pairing between X and Y prime. Since Y prime is equal to the restriction of X prime on the subspace, the closed subspace Y. So if the argument is in capital Y, then the function values, or in other words, the duality pairings, coincide. However, we know that, okay, applying the definition of duality pairing, or the definition of the canonical embedding, okay, in Y, we have this. Since this is true for any element in the dual space of Y, thus we can say that these two are the same. So jy of X is in Y, take note, is equal to Y double prime in this by dual space of Y. Okay, hence the canonical embedding in the closed subspace Y is also surjective. Hence Y is reflexive. So with respect to a subspace, a closed subspace, reflexivity is preserved. Also, reflexivity between Banach spaces is preserved under an isomorphism. And this is our next theorem. Consider two Banach spaces, X and Y, and a bounded linear operator, say T, which is an isomorphism. Then X is reflexive if and only if Y is reflexive. So once again, reflexivity is preserved under a bounded isomorphism. Let's start with the remark that according to the Banach inverse theorem, okay, a bounded linear operator that is invertible has a bounded inverse. Okay, so let us prove this, let's say, implication here. Let us suppose that the domain is reflexive. So we have a map from X to Y, bounded, linear, and bijective. So a typical element of the dual space of X uh, maps X to R, and a typical element of the dual space of Y maps Y to R. Okay, on the other hand, an element X double prime is a map from X prime to R, and similarly a map from Y prime to R is an element of your bidual space. Okay, so let's start with an element of the bidual space. We would like to define an element, let's say X double prime, as follows. So X double prime of X prime is equal to, so I want to apply this to Y double prime. So I need an element of Y prime. So what we can do here is that we can take, let's say, the inverse. Okay. Then this inverse followed by X prime. So it must be the other way around. Is an element of Y prime. Of course, the composition of two linear maps is again linear, and the composition of two bounded maps is again bounded. Okay. So this map is well defined. And if, let's say, if I take this is linear, okay, and you can easily see that due to this part here. And if I take and if we take an X prime with dual norm less or equal to 1, then we could see that estimating this one here. So you have the following product of norms. And as we know, the product of the composition, the product is less or equal to the product of the norms. Here, by product of operators, we mean the composition. Here, we take T inverse as a bounded linear operator from Y to X. So let us correct this from Y to X. So this is less than or equal to T inverse L of Yx Y double prime. Okay. This estimate shows that X double prime is bounded. Since it is linear, it must be in the Duval space. Now, according to the reflexivity of x. If we define x to be the inverse image of the canonical embedding corresponding to x, which is well defined because J would be an isomorphism. Given, again, an element y prime of the dual space of y, okay? If we let, let's say, x prime to be so we take the composition of t followed by y prime. So t followed by y prime. And this is an element of x prime. Then we can now compute as follows. So this duality pairing is equal to, so solving for x prime here, you apply t inverse both sides. So you have x prime t inverse y double prime. However, according to the definition of x double prime here, you will have x prime, x double prime. And since x here is the inverse image of x double prime, this is nothing but x, the duality pairing of x and x prime. What is x prime? That is y prime of t. And you can easily see that this duality pairing can be, okay, you apply t first and then you apply y prime. According to the definition of jy, okay. So this means that we have y prime jy dx. So here we applied the definition of the canonical embedding with respect to y. So therefore, y double prime is equal to jy at tx. And this tx is, of course, an element of y. So that y is reflexive. Okay. So if the domain is reflexive, then the range is also reflexive. Well, the converse is easy since you apply the earlier proof to the isomorphism. Now the inverse. Okay. Since this is a bounded linear operator, it's also an isomorphism that is at the inverse. So if y is reflexive, that's the domain, then the range, which is in this case x, must be also reflexive. So for our next theorem, we will show that reflexivity is preserved with respect to duality. So X is reflexive if and only if its dual is reflexive. So let's start with this direction. Suppose that X is reflexive. So what is the goal? We need to show that X prime is reflexive. So in other words, the canonical embedding of X prime to the bidual of X prime. Okay. And we denote this by X triple prime. However, recall that the bidual is defined as the dual of the dual. And you can recognize that this is the bidual. Okay. So here duality is somehow associative. So this is also the dual of the bidual. So we need to show that this is surjective. Okay, so to do this, let us take an element in the code in the range. Okay, X triple prime. So let us define an element. Let's say X prime by. So if I have an X prime here, it must take an argument in X. So we take the canonical embedding with respect to X. So this is now an element of the dual space of X. Here we take X triple prime. As we said, this is an element of X triple prime, but we know that this is an element of the dual of the bidual. So this pairing makes sense, and you can verify that it is indeed bounded in linear. So this X prime is bounded in linear. And with this, we can now conclude that, okay, or before concluding, let us do some computation. Then for each element in the bidual space, take note that I can write this as what? Jx inverse. Well, X is reflexive, so this canonical embedding is an isomorphism. So you can see here, replacing X by this inverse image, okay? we have Jx inverse of x double prime x prime. Applying the definition of what? Of the canonical embedding. So we have x prime j of x inverse x double prime. Okay. So if you interchange the two and make it a duality pairing between x prime and x, you should apply to the second argument the canonical embedding. And this is now what? X prime, x double prime. Since we have this, okay, applying the canonical embedding for x prime. So this is x double prime, jx prime, x prime. So this is true for each x double prime. So this must be the same as this. So thus, x triple prime is the image, or is an image of an element of the canonical embedding for x prime. So that indeed the dual space is reflexive. So if x is reflexive, then the dual space is reflexive. For the converse, okay, suppose that the dual of x is reflexive. We want to show that x is the primal space, x is also reflexive. So let us apply this, okay? If x prime is reflexive, the dual of it, which is x double prime, is also reflexive. Since the map Jx, okay, from x onto the image, okay, this one is an isometric isomorphism. We know that for any Banach space X, this is an isometry. So we only need to restrict the range in order to have an isomorphism. So this is an isometric isomorphism. Now, this implies, okay, you can prove that isometric isomorphisms maps closed space into a closed space. So in particular, this one is a closed subspace of x double prime. Since x double prime is reflexive, and we know that closed subspaces preserve reflexivity, the image is reflexive. And take note, okay, we have here an isometric isomorphism between x and jx, the image. If one, so if it's either the domain or the range is reflexive, then the other must be reflexive. So in particular, since the range is reflexive, this implies that x is reflexive. And this is the converse of the theorem. So once again, for a Banach space, reflexivity is preserved with respect to duality. Let us state as few examples. So if P is finite and it is greater than 1, then LP omega is reflexive, where omega is an open subset of Rn. And you can apply this by using the, let's say, Riesz-Fischer theorem. On the other hand, L infinity, the extreme cases, L1, RCA K is compact, and C, okay. These are not reflexive. Let us also add WK infinity, W1 infinity, or WK1 are not reflexive. Here, you can also add the Sobolev spaces, K being a positive integer. For the Sobolev spaces, you can embed. There's a natural injection into a finite product of a Lebesgue, Cartesian product of Lebesgue spaces. And for that, reflexivity of this Sobolev space will follow from the previous theorems and the reflexivity of LP. As long as P is greater than 1 but less than infinity. A special kind of or type of reflexive Banach spaces are Hilbert spaces. So a Hilbert space is reflexive. I will not provide the proof since we have done this several times now. The proof for the proof, use the Riesz representation theorem. Or if you like, you can look at our course notes. So we are now ready to prove the following version of the Banach-Alaoglu theorem. For reflexive spaces. So let X be a Banach space. Then, okay, instead of looking at the closed unit ball in the dual, we look at the closed unit ball in X. So if X is reflexive, then this closed unit ball is weakly sequentially compact. So in particular, by a scaling argument, any bounded sequence in a reflexive space has a weakly convergent subsequence. So let us take a sequence in the closed unit ball in X, and we wish to construct a subsequence that is weakly convergent. Let us denote by Y, okay, the closure of the linear span of this space. Of course, the closure is taken with respect to the strong topology. This implies that, okay, Y is separable. So a countable dense subset is any what? Can be a subset of this sequence. So this is separable and closed. In X with respect to the strong topology. So being a closed subspace of a reflexive space, Y is also reflexive. Moreover, this implies that the canonical embedding from Y to Y double prime is an isometric isomorphism. It follows that, okay, the dual space, okay, is reflexive and separable. Okay, so let me state this as a lemma. If you have, let's say, a Banach space, let's use a different notation. So let Z be a Banach space. If the dual is reflexive, then the primal space is also reflexive. Okay, first, an isometric isomorphism preserves reflexivity and separability. Okay, so the following lemma states that for a Banach space, if the dual is reflexive, then the primal space is also reflexive. So based on this, and also the proof can be seen, for instance, in the course notes. So I will leave the details for you to check. Nevertheless, continuing the proof, so applying previous lemma to, let's say, z equal to y prime. Okay, we know that y prime is separable. So according to, let's say, the Banach-Alaoglu theorem, okay, for separable spaces, okay, the ball, okay, the closed unit ball of by double prime is a weakly star sequentially compact. Okay, so let us consider yn double prime to be the image of jy xn. Here xn is also in the closed unit ball of y, since the norm in x and the norm in y are the same. So if yn double prime has a, or if xn has a norm less or equal to 1, the fact that jy is an isometry implies that yn double prime is in the closed unit ball and by double prime. For a for some subsequence, applying this weak sequential compactness of b sub y double prime. So let's say I have the subsequence y and j double prime converging weakly star to y double prime. With, of course, the limit is still in the closed unit ball of y double prime. So we wish to prove some limit here. So we now take our candidate limit for the subsequence to be x, and this is what? Let's say this is j y inverse of y double prime. This makes sense since jy is an isometric isomorphism. So the inverse is well defined. Okay, so in this case, being an isometric isomorphism, so it preserves the norm. So therefore, since y double prime has a norm less or equal to 1, x also has a norm lesser less than or equal to 1. So it is in the unit ball in X. Okay, or if you want, it is in the closed unit ball of Y, okay, which is a subset of the closed unit ball in X. Okay, so given, let's say, an element Y prime in the dual space, this weak star convergence, okay, can be written as follows. So Y prime, Y and J, this tends to Y prime, Y double prime. Now, since X and K, these are all in the closure of the linear span. So this is in Y, okay? And I should use J here. We have, okay, the following. So let us do the succeeding computations. So let's start with this duality pairing. Apply the definition of the canonical embedding corresponding to Y. This makes sense because X and J, X sub N sub J is in Y. And this is the same as what? Y prime, using the definition of Yn double prime. So here we have Yn double prime sub J. Okay, we apply this. This tends to, as n goes to infinity, Y prime, Y double prime. And this is equal to, okay, applying the canonical embedding, let's say, this is equal to Y prime Jy or applying this, yeah, taking the image both sides, okay, Jyx. However, this is the same as what x times Y prime. Since x is in Y, so this makes sense. Okay, so we have that convergence for every element in, let's say, Y prime. So, in other words, X and J converges a weakly star or weakly to X. However, our convergence is only with respect to Y at this point. So to leave this weak convergence to the whole space of X, so let us take an element, okay, in the dual space of X. The restriction, of course, on Y yields a bounded linear functional on Y prime. And if I use this as my Y prime here, okay, we have the following. So x and j, x prime. And this is the same as x and j restriction, since the terms of this sequence lies in y. This one tends to x, x prime, y. Again, x being an element of y, this is the same as the duality pairing. Okay. Since this is an arbitrary element of the dual space, we know that this is equivalent to saying that x and j tends to x weakly in the whole space X. So we have constructed a subsequence that converges weakly to some X in the closed unit ball of the Banach space X. And this is what we meant by, of course, again, weak sequential compactness. Any subsequence in the closed unit ball has a convergent subsequence, but with respect to the weak topology. As before, this implies that a bounded sequence in a reflexive Banach space has a convergent or has a weakly convergent subsequence. And this is the end of the lecture. There's also a consequence of this for special subsets. Okay, so relaxing the case of the closed subspace. Let's say, suppose X is a Banach space. And I have a non-empty subset that is closed and convex. So here we replace the subspace assumption by convexity. Then a C is weakly sequentially closed. That is, if I have a sequence xn and C, and xn converges weakly to X, then the limit must be also in C. So closeness, sequential closeness refers to the weak topology. And the proof requires a version of the Hahn-Banach theorem namely the separating hyperplane theorem. So geometrically, now this means that if I have, let's say, a closed convex subset, okay, suppose this is C, and you have a point x not in C, then there must be a hyperplane, okay, that will separate the two. So there, that hyperplane, let's say, is determined by an element of your dual space. And this follows from the Han-Banach theorem. So a sketch of proof for this theorem, why we need the separating hyperplane theorem, is provided in the course notes. So this particular example is useful in or can be used in optimization in Banach spaces, in particular convex optimization. Another well-known theorem or result is Mazur's lemma. So if I have a sequence in a Banach space, okay, that is weakly convergent, then the limit lies in the convex hull, or I should say the closure of the convex hull with respect to the strong topology. So here, this is the convex hull of your sequence. And its definition is the following. So it is a linear combination, let's say, of lambda k xk, k from 1 to m, such that okay, let's define this for a more general set. Okay, so the convex hull of a set A is as follows. Okay, so it just take a linear combinations, or I should say convex combinations. So here the coefficients are positive, they sum up to 1, and the x sub k's are in A. Of course, k is a positive integer. And this convex hull can be shown to be the smallest convex subset containing subset of X containing A. So the proof is quite simple. You take, let's say, a C to be the closure of the convex hull in the previous theorem. So take note that the C is obviously closed with respect to the strong topology. The closure of a convex set is again convex. So you have this property. So it is weakly sequentially closed. So you can apply the previous theorem to establish Mazur's lemma. So once again, For a weakly convergent sequence, the limit is always an element of the closure of the convex hull of your sequence, and the closure is taken with respect to the strong topology. So in other words, it is possible to choose a subsequence that are finite linear combinations of your original sequence. And then with that new sequence, you have convergence with respect to the strong topology. And that's it for this lecture. See you on the next one.